All right, so now in this video, we're going to figure out how to actually use our formulas in order to find volumes of revolution. I keep saying volumes of revolution without actually describing it very well, but volumes of revolution is you have some line, some curve, and you're going to take that curve and rotate it around that line. So we're going to rotate this around, that gets us a circle, rotate this around, here's a circle, and that'll basically make a vase that looks like that if you turn your head to the side. So we're taking this thing and revolving it around to make this vase. It's not a vase because it's all enclosed, it's not an opening. But the basic idea is you're making this solid structure by rotating this two-dimensional area all the way around some line. So our first method is the disk method, which is pretty much the method we described in the previous video. You're going to do the integral from the start of your solid to the end of your solid, and then pi r squared is the area of all the circles you're adding together. All right, so find the volume of the solid generated by rotating the region bounded by y equals the square root of x and the x-axis over that interval. So let's draw a picture first. All right, so the square root of x function just looks like that. All right, the area bounded by the square root of x and the x-axis, so we're looking between those two things in the interval 1 to 4. So 1 to 4. All right, so this is the area we're talking about, our two-dimensional area. And then we're going to rotate that around the x-axis. So we're going to take this area like this, rotate it around. Again, that's going to create a kind of bigger circle here, a smaller circle here. So you're going to get this solid shape that looks kind of like that. All right, trying to find the area of that shape, three-dimensional shape. It's always hard to picture 3 dimensions when you're writing it on paper, but that's the basic idea. So we find this area, we rotate it around to create this big solid shape, kind of like that picture there. We saw to do this, we basically add up a bunch of circles. That's obviously all we're doing. We're stacking an infinite amount of circles on top of each other, and that creates a volume. All right, well, our thing starts at 1, ends at 4. That's told to us in the problem. And each circle has an area pi. R is going to change. It's not always going to be the same r, but it's told to us that the height is the square root of x squared dx. So that's the formula. You basically put the starting and ending point of your solid in the integrand. Whatever the radius is, which is normally just going to be given by a function, you put in there. And now it's just simplifying. All right, add 1. Again, remember pi is just a number, so don't try to treat pi like a variable. So we're going to add 1 to the exponent, divide by the new exponent, and evaluate that from 1 to 4. And again, I'll pause the video here and just kind of work out the values, and then we'll look at the final answer. All right, so I did the calculations, and you can see the final answer that we get is going to be 15 pi over 2. All right, so that's the volume of this rotated area. All right, that creates this kind of, I think it kind of looks like a drum or something like that. All right, but this solid right there, all right, the volume of that would be 15 pi over 2. All right, so the basic idea is just identifying the initial area that you're going to rotate and then just putting into this formula. Again, it's the kind of bounds, pi r squared, and it's just figuring out an integral from there. All right, the real only way to change this type of problem is instead of rotating around the x-axis, we're going to rotate around the y-axis. All right, so find the volume of the solid generated by rotating this region bounded by the x-axis and the y-axis. So let's draw a picture first. All right, 4 minus x squared is going to be a upside down parabola. And we want it to be bounded by the x-axis and the y-axis. We're looking at this area here. But again, instead of rotating around the x-axis this time, we're going to rotate it on the y-axis. So we're going to get this bigger circle on the bottom. We're actually just going to get a single point on the top, and that's going to give us this type of shape. Oops. All right, so kind of like a bell. Right? Maybe not exactly a bell, but that's a good starting point for the area we're trying to find. All right, but again, the idea isn't going to be much different. The only difference is, just like when we were finding the area between curves, now we're thinking about it in the y direction, because we're rotating on the y-axis. All right, so we need to figure out first, if we're thinking about it in this direction, we need to change our equation to be x equals instead of y equals. So the first thing we're going to do is get x squared is 4 minus y, and take the square root of both sides. Because whenever we're working in the y direction, we want an x equals equation instead of a y equals equation, because we're changing the angle that we're thinking of. But everything else is still going to be the same. We're still going to take our integral from the starting point. Again, our y-axis is our starting point at 0, up to that top part of the y-axis, which is at 4. And then it's pi r squared, so pi times 4 minus, oops, not 4 minus y, the square root of 4 minus y. Squared, and the y in this case, because we're doing it in terms of y. All right, so same thing, pi r squared. The only difference between this example and the last example is we're doing it in terms of y and instead of terms of x. So first, simplify a bit. All right, we can bring the pi out to make it a little bit easier. And then we're going to take the antiderivative. The pi is going to stay at the front. Our antiderivative is going to be 4y minus y squared over 2. And then we're going to evaluate that on our bound, 0 to 4. All right, so again, once again, I'll pause the recording here, plug in all the numbers, and just see what the final answer is. And once we plug all the numbers in, the zeros nice goes away. We get 8 pi as our final answer. All right, so these are our two methods for finding the volume of a solid generated by rotating a region. If we do it in the x direction, we just set up an integral. We do pi r squared with the r. The radius is given by whatever our function is. If we want to rotate around the y-axis, we just have to make sure that we change our equation appropriately, so it's x equals instead of y equals, but then it's the exact same thing. It's pi r squared is the area of each circle that's generated. And again, the integral is basically just adding up this infinite number of circles to give you a volume as your final answer. That's the first method for finding the volume of a solid created by rotating.